Today, we are going to take a look at the hypergeometric distribution. So let's dive right in and start with example number 1. Determine the probability distribution for the number of women on a 4-person committee to be chosen from 5 women and 7 men. Well, we're talking about committees, so the order doesn't matter. And we're also assuming that one person can only take one position. So that as soon as a person is chosen, then that person is no longer returned to the pool. They've been used, right? So let's take a look. We're going to let X represent the number of women on the committee. That is going to be our random variable. Oops. And so for our distribution, you have to think of all the possibilities then when you want 4 people to be on the committee, and we're having X represent the number. So the first possibility is that there could be a 4-person committee with no women. And then what is the probability of having that? Well, out of the 5 women, you want none. So that means out of the 7, you want 4. And if there's no restrictions, this is what we call the no restriction case in the denominator, there are 12 people and 4 of them are going to be chosen on the committee. That is the no restrictions case. Okay, and then you can use your calculators to do this choosing. It's a 5 choose 0 times a 7 choose 4, all divided by a 12 choose 4. I believe that comes out to be 35 over 495 or 0.0707 repeated. And that would be the probability for having no women on the committee. So then we're going to adjust it slightly. What if you end up with 1 woman on the committee? So that would be a 5 choose 1, that's your 1 woman, times a 7 choose 3. So then if there's 1 woman, there must be 3 men. And it's still a 12 choose 4 on the bottom. So then that'll be a 175 out of 495, and that would equal 0.354. So we're well on our way for our distributions. So we still have to do for 2, for 3, and for 4. And it follows the same pattern. And you can do your calculations to get your fractions or your decimals. And that would be the probability distribution. So in case you didn't notice, a hypergeometric distribution involves a series of dependent trials because what is chosen in the first round affects the next outcome, the next person you choose to put on the committee. We still have 2 outcomes, either success or failure, and the probability of successes changes with each trial. And the random variable X is the number of successful trials that you want in the experiment. That is always the X. So the probability for hypergeometric distribution has this distribution, where A is the number of successful outcomes, X is the number of successes that you want, and then you have N minus your A over R is the total number of trials minus X, all over an N choose R, or what I like to call the no restrictions case in the bottom. So lots of variables going on there, but it's more like the pattern that I showed you on the first example. But this is good to have, and good to have is your formula. Let's go through another example here. We have Joe and deals 5 cards to Sally. And what is the probability she has at least 4 spades in her hand? Did you see it? Did you see it? At least. What should you consider if you're doing at least cases? Maybe the indirect? Well, let's see. We're going to let X represent the number of spades. So A is going to be the total number of spades in your deck. So that is 13. Remember, there's 13 beach suit in a deck of cards. X is going to be the number of spades that you have in your hand. R is the number of cards that are dealt. In this case, it's 5. N is going to be the total outcomes, which is 52, the 52 cards. So we want the probability that you have at least 4 spades in our hand. So you can have 4 and you can have 5. Those are your 2 cases. So if you have 4, you would 4 spades, that would be 13 choose 4 times 31 choose 9. 39 comes from the remaining non-spades. So if 13 are spades, 52 minus 13 is 39 cards that are not spades, and you need to choose one of them, so you end up with 5 in your hand. And there's a quick check. You can do 13 plus 39 gets you your 52 in the bottom, and 4 plus the 1 gets you your 5 on the bottom. So that's how you can do a quick check. So this is a probability where you have 4 spades, and then for 5 spades, it's a 13 choose 5, technically times a 39 choose 0 over a 52 choose 5. And that is just to keep your check going here. And again, the denominator is what I call the no restriction case. And it should come out to be 0.0107 plus a 0.0005, which is a 0.0112. Okay, if you want it, so this is the direct way. If the indirect method would be 1 subtract, the probability you get no spades, 1 spade, 2 spades, and 3 spades. So the indirect method would be not as efficient as doing the direct method in this case. So there is an expected value quick formula. Instead of doing out your full probability distribution and multiplying and adding it all together the long way, the expected value for a geometric distribution is just R times A divided by N. So in that last example, what would be the expected number of spades in Sally's hand? Well, we have X being the number of spades, review of what R, A, and N is. Okay, I think I've got my brackets way too big here. You have to do 5 times 13 divided by 52, so that is going to be 1.25 spades. But really, this could work for any suit because you have 13 if you wanted 5 cards in your hand. So on average, you would get 1.25 spades in your hand, or that's what you can expect to get in your hand of 5 cards. One more example here. We've got a jar containing 20 red and 30 green jelly beans. It's Christmas. What is the probability that at least 2 are red when you draw 10 jelly beans from the jar? Okay, so let X represent the number of red jelly beans. So we've got A equaling 20, that is the total of reds. R equals 10 because we're choosing 10 jelly beans from the jar. N equals 50 because you've got 20 plus 30, you have 50 jelly beans in your jar. And we want the probability that at least 2 are red. So we want the probability that X is greater than or equal to 2. And take a look at the notation here. This is how you write it. So this would be good if you did the indirect method because to get at least 2 red, you could get 2, 3, 4, 5, 6, 7, 8, 9, and 10. Way too many cases to calculate. So the opposite cases that you do not want are when you have no reds or when you have 1 red. You're going to take both of those cases away from 1. Now we just need to calculate using our nice formula. We want no reds. There's 20 reds, no reds, so all 10 jelly beans must be from the green, so it's 30 to 10, divided by your no restriction case, which is 50 jelly beans, choose any 10. Okay, and then we're subtracting also the case where you have 1 jelly bean out of the 10 that is red, so we want 20, choose 1, that will be your red jelly beans. That means we need 9 green jelly beans, so 30 choose 9. You'll multiply those 2 and divide out by your no restriction case of 50 choose 10. So your no red jelly bean case probability should be 0.003, and your 1 red jelly bean should be 0.028. Take those both away from 1, and you should get 0.969. Okay, and what would be the expected number of red jelly beans? So we just need here our 10 times 20. because R is the number of jelly beans we're choosing, A is a red jelly beans that we want, and N is 50, the total number of jelly beans. The other way you can think of it is you can take the probability of getting a red jelly bean and then times it by the 10 trials. Probability of getting a red is 20 out of 50, and we're multiplying by our 10 trials. That's another way to think of it, and some people have more success thinking of it that way. And then when you do those calculations, it would be 4. So out of your 10 jelly beans, you should expect 4 of them to be red. And that is how a hypergeometric distribution works. So remember, the biggest difference with the hypergeometric is that the probability changes. The trials are not dependent at all. If you have any questions, send them my way. Thanks.